So coin change 2. You're given an integer array coins, but basically it maps to the nums array, the previous problem. And you're given an integer amount, basically maps to the target variable in the previous problem. You want to return the number of combinations that make up that amount. And again, it's a loaded term. Here the combination literally means subsets. Again, you don't need to worry about taking mod and all. The final answer will be will not have an overflow, will not give an overflow error. So let's uh, go through this toy example. So suppose you have an amount of 5 cents, and you want to make it up using 1 cent, 2 cent, and 5 cent coins. So you could take a 5 cent coin, or you could take two 2 cent coins followed by 1 cent coin, or you could take a single 2 cent coin and three 1 cent coins, or you could take 5 1 cent coins. But as you can see here, this 2 plus 2 plus 1 is no different from 2 plus 1 plus 2 or 1 plus 2 plus 2. In the previous problem, these would have been counted as separate ways of making up 5 cents. Same way here, we would have 1 2 1 1 would be different from 1 1 2 1 or 1 1 1 2 or 2 1 1 1. So that's the requirement here. We have to focus on subsets of coins literally instead of linear arrangements where order matters. Second toy example, we want to make up 3 cents using only 2 cent coins. There's no way to do that, so the answer is a 0. So, questions about the problem statement? Surya Prakash?
Hi, Omkar. Yeah, I was thinking like this is same as the previous one, and we can loop the coins first, then the amount, right? So we are only looping like a single coin multiple times, and then go for the different coin.
Okay, maybe that's where we'll end up, but we'll go through the thought process.
Okay.
Right. So if I hadn't solved this problem before, I can, there's very little chance that I would have understood what you said. So that's why I don't want to directly talk in that language. I'll start with the basic problem solving strategies, and then as we optimize our way through it, we'll probably end up where what you're talking about.
Sure. Yeah. Thank you.
So let's again take a minute or two to reflect on this. And I'll go through my thought process and then take questions. Course approach of exhaustively enumerating all subsets clearly will be exponential in time complexity, because there will be an exponential number of subsets to be enumerated or tested. So we want to do better than just enumerate everything and then check which of them satisfy the constraints. So let's try a decrease and conquer approach. Now, if I ask, like I did in the previous problem, what's the last coin? As a lazy manager, I focus on the last coin. Now, one of the issues, well, the main issue is that this problem is different from the previous problem in that the arrangement of coins does not matter. So in the previous problem, if my last coin was, let's say, a 1 cent coin, or maybe it was a 2 cent coin, right? And then maybe for my left subordinate in the last problem, uh, maybe the penultimate coin was a 2 cent coin, and maybe for this subordinate, the penultimate coin was a 1 cent coin. So whatever whatever solutions these two subordinates got, so they are identical subproblems. So whatever solutions they got, they must be identical. But extending each of those solutions by 2 cent, by a 2 cent coin and a 1 cent coin, and or by a 1 cent coin followed by a 2 cent coin, there is no for this particular problem there is no distinction between uh, this. And so the problem with focusing on the last coin is that we focus only on this, right? If I, as a lazy manager, focus only on this and then I hire subordinates under me, my left subordinate will focus only on these two choices, and same with my right subordinate. So at each level in this management hierarchy, each manager is focused only on uh, choosing one of those different denominations. But across the hierarchy, we see that there is redundancy, there is duplication going on, because my choosing a 1 cent coin and my left subordinate choosing a 2 cent coin is no different from my choosing a 2 cent coin and my right subordinate choosing a 1 cent coin. So they are identical subsets even though we treat them differently. If you have done or if you remember the class on combinatorial enumeration, you might remember that there was a problem where we had to enumerate all subsets where there were duplicates present. Right? For example, your set might have been something like 1, 2, 2. So if it's 1, 2, 3, clearly there would be 2 to the power 3 or 8 subsets. I think that was the subsets 1 problem which you must have done in the combinatorial enumeration class. But then there was an extension of it. I'm not sure if your instructor did it, but I do it in my alternate uh, instructor video for that class. The number of distinct subsets is not going to be 8 here. It's going to be something less. So if we blindly followed the subset solution, subsets 1 solution, where we enumerate all the subsets, we will end up enumerating the same subset multiple times, because wherever there was a 3, we just change it to a 2. So in that case, uh, different subsets are going to collapse together. For example, if this was 1, 2, 3, then there would have been one subset of the form 1, 2 and another subset of the form 1, 3. But since there is no 3, there's only a 2, the 3 is replaced by a 2, these two subsets become identical and so they would collapse together. So I don't know if you remember how to resolve that. So the problem here is that I am making a local decision at my level about the 1 cent coin. My subordinate makes a local decision about the 2 cent coin. or I could make a local decision about the 2 cent coin, and my subordinate at the next layer makes a decision about the 1 cent coin, and that introduces redundancy. So to eliminate this redundancy, we don't want this kind of structure where each manager can independently choose what coin denominations uh, to pick at each level. Instead, if we imposed an ordering on these denominations and said that I, as the top manager, the root manager, will focus only on, let's say, the 1 cent coin, but I will decide how many 1 cent coins to include in the subset. So I might decide to include one copy, I might decide to include 2 copies, 10 copies. So for this subsets problem, I might decide to uh, include the twos in the subset. So, but for me, the choice of including or excluding a two is not a binary choice. I could exclude any two, or I could include one two, or I could include two twos. But I am the one who's deciding how many twos go in. And nobody below me, no layer below me is going to make a decision about the twos, because it's at my layer, it's at my level that decisions about the twos are being made. So this will make sense if you have solved that problem, and I'm kind of assuming that you've solved the subsets 2 problem, where to prevent this kind of redundancy where 1 followed by 2 is the same as 2 followed by 1, we impose some ordering between the 1 and 2. Doesn't matter whether 2 comes after 1 or 1 comes after 2. What uh, what we want is, um, let me actually take an example. Suppose my target amount is 32 cents, and my coins array has a bunch of coins, but let's say 1 to 5. So when I, as the root manager, am looking at a target amount of 32, I'm not going to make decisions about each of the coins. Right? The question that I was asking in the previous problem was, what's the last coin? So here, instead, I'm going to change that question slightly. I'm going to say, uh, instead of looking at multiple different denominations or any different denomination of coin, I'm going to focus on only one denomination and focus on how many copies of that denomination to include. So you can say, how many copies of the last coin should I include, right, in the subset that I'm building? Obviously, I have to make all the choices. So if I have a target, so in the subsets 2 problem, if I had 2 copies of the 2, maybe I choose 0 copies, maybe I choose 1 copy, maybe I choose both copies. So I have to make each of those choices independently, one after the other, and then depending on whatever partial subset is built up, my 3 subordinates will further extend it with other values. So in a similar way, if I have a target amount of 32, um, how many copies of the last coin? So let's say the last coin is 5 for me. It could be 1. Doesn't matter what the ordering is. They're all unique numbers. So let's say I focus only on the last coin, which is 5. And I'm going to make the decision for how many copies of 5 go in. So maybe there are 0 copies of 5 that go in. So, uh, so maybe I exclude the 5, in which case the subordinate I hire will have a target value of 32, and my subordinate will then focus on the remaining coins 1 comma 2, and again at his or her level will focus only on the last coin in that uh, list. So maybe the 2-cent coin. How many copies of the 2-cent coin should go in? That's what my left subordinate will decide. But at my level, let me just focus on what I have to do as a manager. Uh, I could decide to include a 5, but include 1 copy. If I include 1 copy of 5, I'm going to have a remaining amount of 27. Uh, and then I'm going to ask my subordinate to take over that amount and figure out based on the remaining coins how many subsets make up that. Or maybe I could pick 2 coins, 2 5-cent coins, in which case my remaining amount would be 32 minus 10, which is 22. Or maybe I could pick 3 copies, in which case this would be 17. Or maybe I could pick 4 copies, in which case this would be 12. Or maybe I could pick 5 copies, amount of 7. Or maybe I could pick 6 copies, in which case this would be 2. If I picked 7 copies, then the remaining target amount would be negative, which is not a valid amount. So I won't make that choice. But I'm making the decision about uh, not just what the last coin is. Right? This question is being asked, but um, instead of picking 1 coin, I'm making the decision about all the copies of that coin, so that nobody under me um, is even looks at that coin. And that's how I get rid of this redundancy, where I look at 1, somebody below me looks at 2, uh, and then I am also looking at 2 and somebody below me is looking at 1. So the 1-cent coin is being looked at different levels in the hierarchy. So is the 2-cent coin, which is where the redundancy comes in from. Okay, so this is basically the 5-cent coin level, decisions about the 5-cent coin. You can call this multi-way inclusion. I'm not sure if that's an official word, but at least that's what I call it. And so if let's say this subordinate tells me that looking only at the 1-cent and 2-cent coins, there are maybe 10 ways of making up this amount. This subordinate tells me there are maybe 8 ways of making up that amount. Then I know that to all of these 10 subsets, I could add nothing more and end up with a subset or end up with 10 subsets which also add up to 32. From my second subordinate, if I learned that there are 8 subsets made up, constructed from the 1-cent and 2-cent coins with with a target amount of 27. Each of those 8 subsets can be extended with one more 5-cent coin to make up a total amount of 32. So we are still adding the counts from all our subordinates. Right? We're still adding the counts. Um, Any questions about this? Now, for this problem, it turns out there will be at least 3 or 4 different solutions we are going to end up examining, but the starting point for all of them is this. So this is the uniform thought process, and you'll see that there are going to be different, slightly different ways of implementing this. So think about what the problem description for an arbitrary worker in this hierarchy is. An arbitrary worker in this hierarchy is being given an amount and also a prefix of the coins array. They're not going to look at all the coins. They're going to look at only a prefix to avoid that duplication. So the problem description will be given an amount, let's say A, and a prefix of this original coins array, let's say coins from index 0 to I. The total number of subsets adding up to the amount A from the coins, well, from the coins with index 0 through I. Okay, from this prefix of the coins array. That becomes my general problem description. Now the question is, how do I solve this? Should I solve it recursively? Well, let's think about it. In a general coins array, uh, let's say we have coins 1, 2, and 5. Um, if I follow a path from here where I included, well, where I excluded the 5 and this subordinate included, let's say, 5 copies of the 2-cent coin. Right? So I did not include any 5-cent coin. My subordinate included 5 copies of the 2-cent coin. So effectively at this level, the target amount is reduced by 10 cents. Right? It's 22 or something. Let's look at another path where I included 2 copies of the 5-cent coin, and this particular subordinate excluded any 2-cent coin. So think about the subproblems that these two managers are given. They're both given the same target amount, just 22 cents, and they are asked to look at the same prefix of the coins array. In this simple example, there's only a 1-cent coin left, but in general, you can imagine that array being much longer. So there'll be potentially many coins for them to look at, but they're looking at an identical sequence of coins, an identical prefix of the coins array with an identical amount to be constructed. So clearly we have overlapping subproblems. And this leads us to concluding that we should use dynamic programming. So if we were to merge all the redundant nodes in this corporate hierarchy, how many distinct subproblems are we going to get? So the number of distinct subproblems in our dependency DAG is going to be the number of ways of number of different values that the first parameter can take, which is which is essentially 1 plus a, you can say, because the amount can be the original a, the original amount, which was actually a variable called amount, or it could be amount minus 1 or amount minus 2 all the way down to 0. So there are amount plus 1 ways of fix different values for the first parameter. How many different values are there for I? Well, if we have the coins array of length n, then uh, there are so the values that I can take will vary from 0 to n minus 1. So n different values. Right, and depends on what your base case is. It could be n or n plus 1. Let's say the base case is could be where you have no coins left at all. So in that case, this would be n plus 1 as well. Otherwise, it would just be n. So the number of distinct subproblems is going to be amount plus 1 times n plus 1. And because these are two parameters independently varying within continuous range from 0 to amount and from 0 to n minus 0 to uh, yeah 0 to n minus 1, but that 0 is not. So when we say 0 to n minus 1, we are assuming that the first coin is at index 0, but I'm saying maybe we exclude even that first coin from our base case. So that would be one additional uh, case to consider. So that would be n plus 1 different values. Since they are both continuous ranges, it makes sense to think of representing this subproblem DAG in a regular way, where we have um, I mean, it could be I values varying along the rows and A values along the columns, or it could be A values along the rows and I values along the columns, doesn't matter. This is our subproblem DAG. And what we are saying is, if we go for this multi-way inclusion kind of approach, then f of a comma I will, let's say this is the manager who's trying to solve f of a comma I. He or she will look at coins of, the ith coin or coins of I, whatever you want to call it, and try to see how many copies of that coin could be included at max, so that the resulting amount is non-negative. However many copies there are, and how do you get the number of copies? Well, you just take the denomination of that coin and look at what the amount you have to make up is. You divide A by the value of that coin. That will tell you how many. If you do an integer division, that will tell you what's the maximum number of coins you can include. So from 0 all the way up to that max value, you will include that many copies. These are the options. And so your f value, f of a comma I, if you want to represent it more formally, would be the sum of uh, so let me just write it here. If there are at max C copies of coins of I that can be included, then f of a comma I is going to be, well, first let me write it in a more expanded form. So the exclusion choice would be f of a comma I minus 1, right? Because the amount remains the same and my subordinate is going to look at all coins except for the coin that I was focused on. Or maybe I include one copy, in which case it's going to be a minus coins of I. That will be the amount. And then that subordinate will look at this prefix of the coins array. Or maybe it will be a minus two copies of the coin I'm focused on, and my subordinate will focus on the remaining coins, and so on. So we can write this as f of a minus, how many copies of the coin uh, are we going to have. So let's say we have C copies in general. C times coins of I, comma I minus 1, where C can vary from 0 for the exclusion case all the way up to the max value, where the max value would be given by the amount divided by the value of the coin. So if you look at this recurrence, in terms of the dependency DAG, so here I've made I as the first parameter, the coins as the first parameter, the amount could be huge. So it looks like a horizontal rectangle. So this, if I look at an arbitrary node here, f of, uh, this arbitrary node is telling me using only these coins from coins of 0 all the way to whatever the ith coin is, how many ways can I make up this particular amount? So if I exclude that coin completely, my amount does not change, but my subordinate would then focus on the coins up to I minus 1. So this is one of the nodes I depend on. If I include one copy, then my amount is going to come down, shift down by 1. Not by 1, by whatever the denomination of that coin was, right? A minus coins of I. But the other parameter would be I minus 1. So this would be the node that I would depend on, and so on. So if I have two copies, I would depend on this node, right, where this amount is A minus, uh, this amount is A minus 2 times coins of I. This amount is A minus coins of I, and this amount is A itself, and so on. But in general, there will be an arbitrary number of coins I could include of with that denomination, the ith coin. So it does look like the value in any for any subproblem depends only on the values above and to the left. So that's clearly a DAG. There's no cycles here. And that also gives me uh, potentially multiple topological sort orders in which to fill in the DAG. Well, firstly, it gives me a representation that I should use a 2D table. Should use a 2D table with the rows corresponding to the coins of different denominations, the columns corresponding to increasing values for the amount. And if I were to fill in this table in any topological sort order, uh, then I would reach any particular cell only after all the subproblems it depends on have been computed. Solutions to them have been computed. And I use them to find the value here. So that's one, the culmination of this thought process. As I said, there will be slightly different ways of doing this, which I'm going to come to, but I just want to complete one complete thought process first. Any questions before I write the code for this? Okay, so let me write the code now. So what are the dimensions of the table going to be? It's going to be 1 plus amount times 1 plus length of the coins array. Well, let's think about what the base cases will be. If the amount is 0, let's think of a table where if the amount value is 0, then it doesn't matter which prefix of the coins array you're looking at. Uh, there's only one subset that can make up that amount, which is the empty subset, since all coin denominations are positive. So I'll write a 1 here everywhere. If the amount is 0, doesn't matter how many, what prefix of the coins array you look at, the amount will be 0. So this is the amount axis, and this is the index, or you can say the coins index in the coins array. Let's just call it coins. Now, what about the top row? The top row, so the question is, should we treat the top row as the leftmost coin, corresponding to the leftmost coin, or should we treat the top row as corresponding to no coin? And if we treat it, let's look at both options. If we treat this as, we treat the top row as, let's say, coins of 0, the next row would be coins of 1, and so on. If we do it that way, then these values here will need to be computed from the recurrence. And when we compute from the recurrence, we see that this I minus 1 is an index that goes back in the coins array. That means we are going to go back to a prefix of the coins array, which is essentially of length 0. Right, so but that doesn't exist because we are assuming the top row is coin 0. So that's a little complicated. Instead, if we just assume that this axis is, let me call it the prefix length of the coins array. Prefix of the coins array. Then we can have a prefix of length 0, we can have a prefix of length 1, 2, so on, all the way to the length of the coins array. right? So this row corresponds to the leftmost coin. This row corresponds to the second leftmost coin. And this row corresponds to the rightmost coin. This top row corresponds to there being no coin. Empty prefix. So if you have an empty prefix to focus on, but a non-zero amount to make up, there is no way we can make up a non-zero amount using an empty prefix. So we can fill all these with zeros. So this is more convenient because I just fill everything with a zero. Left wall is a wall of ones. Um, and now I can start doing my topological sort in this order. So I hope that makes sense. So my table is going to be a two-dimensional table with size n plus 1 times a plus 1, right, or amount plus 1. Let's call it a plus 1. Actually, the variable is amount, so let me make it as amount plus 1. So I should write this as amount and this as a to be consistent with the notation in the problem. Where n is the length of the coins array. So initialization, uh, or you can say the base case is, firstly let's initialize the entire table to 0 so that we don't have to do the initialization of the top row explicitly. So we only have to initialize the left wall, the leftmost column, and that we can do by having our row variable varying from 0 through 0 through n, index 0 through n. We set table of row comma 0 to 1. And then we do our actual traversal using a double for loop. So we say for so we'll have an I variable or a row variable, I variable varying from 0 through n. Right, so that's the index in the coins array. Actually, it's not the index in the coins array because this 0 means that there is no prefix. So in that sense, the index is kind of like -1 there, but so anyway, so the I is the row index varies from 0 through n, and the column index, let's just call it A, varies from column 1 to column amount. And what we do to fill in each cell is essentially apply this recurrence. By the way, notice that the parameters here in the recurrence are switched. So the I parameter is the second one, this one is the first. So So you should read it as f of I comma a to be consistent with the table we've drawn. So we have to do a bunch of summations and store the result in row I column A. So each summation value will correspond to an inclusion of one more copy of the whatever coin we are including. So this row 1 means you're looking at the leftmost coin. This row 2 means we are looking at the second coin from the left, which is coins of 1. This row n means we are looking at the rightmost coin. So if you are looking at row I, we are in general looking at coins of, so this is row I, we're looking at coins I minus 1. It is the ith coin, but the index in the coins array is going to be I minus 1. So when we look at the ith coin and this amount, so we will need to do a summation over all the value over all the copies of that coin that can be included. So what's the maximum number of copies that can be included? Well, we just take the amount. So we are in row I column A. We take the amount A and we divide it by the value of the ith coin, the denomination value. So this is, so now we do a multi-way inclusion. We include as many copies. So for the copy C, varying, so there could be 0 copies all the way up to max copies. Right, this is where we are trying out each of these, making each of these choices and looking back at either this value or this value or this value or bunch of values on the left, but the previous row. So we will take the solution from each of those cells and add it to this cell. So the value in this cell, which is row I column A, will increase by the count that is returned to us by our corresponding subordinate. What's the problem that our subordinate was given? The I value is always I minus 1 because our subordinates are looking at a slightly shorter prefix. The amount value is going to depend on how many copies I included. So if I included C copies of the ith coin, then the amount is going to decrease by C times the value of the ith coin. So we do this, and then at the end our answer should be sitting in so we want to create an amount which is equal to the amount variable using all the coins. So in the bottom right cell, so we return the value in the last row, last column. So the last row is going to be row n, and the last column is the amount value. So that's the multi-way inclusion option you can see that uh, there's actually a triple for loop here. So there's an outer loop from 0 to n, so it's going to run n times roughly. The next inner loop is going to run amount times, but then there's a third loop which runs as many times as the number of copies. And so, any questions so far? I'm going to try to improve on this, but is it clear what the thought process was? Yeah, Subbu.
Yeah, Omkar, can you go back to recursion tree you made, right? Yeah. So there, you see that 1 into 5, 2 into 5, right? So first you took the right side one, 5, while implementing the recursion tree.
Yeah,
So, but when I'm seeing the code, so you started from the left side. How that intuition will generate? Because when I was thinking, okay, how we can should I take from left, from right or left? You know?
it actually doesn't matter. You can take from either side. I do decrease and conquer from the right side, which leads to the solution being built up from the left side, because dynamic programming tabulation is a bottom up approach. So the solutions are going to be constructed for increasing amounts, and for each coin, each successive coin, it's going to be in increasing amounts.
Okay, it's either way it will work, left to right or right.
Yeah, either way works.
Okay, thanks.
Yeah, Raghu.
My question was a little unrelated. It is not unrelated, but related to your subsets 2 point. Um, the way I went about solving subsets 2 was in the include exclude choice.
Hmm.
If the last value that I had put into my subset is a duplicate of the value that I'm looking at, and I have sorted the pre-sorted, sorry, I should say the array,
Hmm.
the numbers, then I don't go into the exclude choice, right? I only go into the exclude path if the last value in my uh, current subset so far is not a duplicate of the value I'm looking at. Does
Okay.
that make sense?
So I'm going to do this in a slightly different way. Maybe what you're saying corresponds to that other way. So here I'm imagining each manager as making a multi-way inclusion choice, where exclusion is basically an inclusion of 0 copies.
Yeah.
So up to the max number of copies. Another
Uh-huh.
so another way to think about this is the following, which could be what you're referring to. So let's say I have an amount of 32 at my level.
Are you
What I
drawing
do is,
something? I don't think I can see.
oh, sorry. So, um, so at my level, I could decide that I'm going to move this here. So, I could decide to exclude the 5 cent coin Or I could decide to include the 5-cent coin. Right? If I excluded the 5-cent coin, um, I'm effectively telling my subordinate that you start looking from the 2-cent coin onwards. Right? But if I include a 5-cent coin, so let me actually move this down a lot. So this subordinate is going to start looking at the 2-cent coin. If I include a 5-cent coin, I'm just going to draw a new type of subordinate here. This subordinate has an amount of 27 and is going to decide whether or not to include or exclude one more copy. So if he or she decides to exclude one more copy, I'm going to come here. So this amount is 32. This amount is 27, or include one copy. Oops. Should draw fictitious. So the amount left is 22. This subordinate could exclude. So this exclusion is like abandoning that denomination. So we could abandon it after including nothing, or we could abandon it after including one copy, or we could abandon it after including 2 copies or 3 copies or 4 copies. 12 or 5 copies. Should be 7 or 6 copies. Should be 2. Yeah, so exclude, 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 exclude. So this would be 22, 17, 12, 7, 2. So a multi-way inclusion can be, if we want to stick to a binary inclusion exclusion choice, instead of having a multi-way fork here, we can actually have a sequence of binary forks where the decision being made is, should I include one more copy? Should I include one more copy? And so on. So this actually might seem to make the tree bigger, but in terms of the code, it makes it easier because all I need to now decide is, should I jump out from that? Should I stop considering the ith coin, or should I include one more copy? So if I was f of a comma I, if that was my problem description here, the problem description here is f of a comma I minus 1. If I made an exclusion choice. If I made an inclusion choice, the problem description is f of a minus, I'm going to call this as the ith coin because it's actually coins of I minus 1, but whatever the ith coin value is. And the set of coins under consideration at this point is still up to I. Now this subordinate might again jump out here and make it f of a minus ith coin comma I minus 1, or could include one more, in which case the problem description here is f of a minus 2 copies of the ith coin comma I. So the advantage of this is now my F value in any cell depends only on two other values instead of a bunch of other values. Now I use just two values. So this can actually make the code a little simpler. Let's go back here. So um, the initialization remains the same. The structure of the for loop, the double for loop also remains the same. But instead of, do it in green, instead of doing this, figuring out what's the maximum number of copies I need and so on, I just make an inclusion exclusion choice. So what is my exclude choice? My exclude choice is that the value in table I comma a is just going to be the value in the, I just jump out of that coin. So I just look at index I minus 1 without changing the amount. So that's like looking, if I'm here, I'm just looking at the value here. So that's my exclude choice. And my include choice would be to include one copy. So uh, I would add to, so whatever the exclude count was, to that I'm going to add the include count, which is going to be what? If I include one copy of that coin, uh, the amount and the index, that is what I have to decide. So the index remains I, right? Because it's like, so the index remains I. It's just the amount that changes to a minus the denomination of that coin. So a minus the denomination of that coin, which is going to be coins of I minus 1. Whereas here, when I make a multi-way inclusion choice, I'm necessarily jumping back to the previous row because I'm jumping out of the zone. Whereas here, I jump out only when I make an exclude choice. When I make an include choice, the amount has gotten smaller, but I'm still in that zone. So my subordinate is the one who will jump out. But we have to be careful here, like we were in the permutations version of this problem, that this should not become negative. So the assumption is that the amount that is remaining is at least as big as the ith coin denomination. Whereas here we automatically took care of it when we computed max copies as this. So we knew what is the maximum number of copies of the coin which can be taken away from the amount so that the value does not become negative. Whereas here, you just have to make sure that the amount is basically this value is greater than or equal to 0. Whatever index we are trying to use is non-negative. Right, so this gets rid of this for loop, and that means we have a double for loop, and this green piece of code is going to run in constant time. So it's going to read one value from here, Sorry, not from there. It remains in the same. So if I include a value, I'm including it from here. This is the I, this is the E choice. So, so it's pretty clear then that the time this will take to run is order uh, n times the amount. Otherwise, you would say it's n times the amount times the max copies. Uh, but with a binary choice, it's just that. Does this connect to what you said, Raghu?
Yes, this is the same thought process. Yeah.
Okay.
Thanks.
Okay, there were.
The only other point I was going to make is this could be a one-dimensional DP table, right?
Yeah, I'm going to come to that next.
Yeah.
Yeah. See if there are questions. Balaji?
Yeah, so I have a question on the how you're calculating max copies. Is that A divided by coins of I, uh, coins of I or coins of I minus one?
Yeah, so the reason I took I of coins of I minus 1 is because I wanted to avoid, treating the top row as because this is going to be a base case. And if I interpret the top row as including the 0th coin, then I would need to write a separate piece of code for what these values should be. They will not all be 0. So uh,
But essentially, you're calculating the max copies for the current index, right? Not for the previous one.
yeah, so the ith coin. So if I am here, I'm looking at the ith coin, which is, or I should say, the prefix of length I. I should remove ith coin here actually. So sorry, I should remove the index I. I should say ith coin. So if I'm at the the row corresponding to the ith coin and the column corresponding to some general amount A. What is the index of the ith coin? It's just coins of I minus 1. Let me remove this arrow so that there's no confusion that the ith coin is that row.
Okay, thank you.
Coins of I minus 1 is the same as the ith coin. Yeah. Pratik? Okay, load your hand. Okay, so
Actually,
like Raghu pointed out, yeah, Pratik.
I just had one question. Yeah.
Yeah.
So, for the solution which you highlighted in the green, are we still using the base case for that 0 coins?
Yes, because as you see here, we are relying on I minus 1 index here. So
If we
so the other way to do it is to not have all zeros here, but start with the 0th coin. But then we would need to make sure that this does not run if I is 0.
right, so if it goes into the negative index, um,
Yeah,
so let's say
it can cause a subtle error in languages like Python where table of minus 1 would be interpreted as the last row.
oh, okay.
So Yeah, so that's why you have to be very careful with this base case here.
So if we don't use the table of I minus 1 and if we just use table of I, then just having first column as the base case, everything else will be taken care of with the main recurrence formula, right?
Right, right. So yeah, you can have a more complicated base case involving only the leftmost coin, and then you have a double for loop, which will calculate according to the recurrence. Or you let even the leftmost coin be handled by the recurrence, but because it appeals to a row above, make sure that the row above is just all zeros.
Right. Okay.
So either of these two is okay, but one of them is a little more complicated.
So the way I had was like I did not have a base case for all zeros. I just had the size of the 2D array as length of the coins array,
Hmm.
and then my first column would be all one like you have here.
Yeah,
But
yeah.
then
So
after
actually,
that,
that's
I start from
yeah,
the
yeah. So
first row, second column.
yeah, so that's where we next move to, which is assume we have the green code, and we know that this uh, is going to be executed in the way that's shown in this diagram. That whenever we come to a cell, we rely on the values on the left and on the uh, cell that's immediately above it. So clearly, we don't need the rows before. In fact, we can even argue that we don't need even two rows. We could just work with one row because suppose this row has been completely calculated. Then the next row, where each cell is going to rely on the corresponding value in the previous row and the value on the left, some value on the left, can be folded onto that row itself, where the exclude case is automatically handled by that because each cell is borrowing the value from the cell above, but if these two rows were folded into one, then the exclude case is already lying there. The include case is something that is uh, added from the cell on the left. So doing that would collapse this 2D table into a 1D table. So we can write the space optimized version for this. So the space optimized version would be um, one where the table is basically a one-dimensional table of size amount plus 1. A 1D table of size amount plus 1. Let's say initialized to 0. Okay. Then the initialization case would be, going back to what's going to happen here. We could initialize everything to a 0, but actually if we take this row and we fold it on that, the only way this row is going to be using the row above is by, each cell is just going to borrow the value from the cell above. And then it's going to start taking the values from the left along with the value above. So um, this value needs to be 1. So when I set table of 0 to a 1, at this point, the table is looking like the top row. Now we start running the for loop as per the blue arrows. So for I in the range from let's see, what was the code here, 0 through, it was 0 through n. So uh, actually this should have been 1. Yeah, because the value of I, if you're talking about the ith coin, the blue arrows start from the first coin and go up to the nth coin. So uh, that's why I changed this to a 1. So I'll just be consistent with that. So ith coin means the first coin, second coin, all the way up to the nth coin. Um, so that's the outer loop, and the inner loop will also remain, the for loop structure will remain the same. For amount varying from 1 all the way up to the maximum amount which is given. We are working with the green piece of code here, binary inclusion exclusion choice. Now the exclude choice does not require special code because the value from the preceding row, same column, is already sitting there in that one-dimensional table. So there's no need to copy it. The include choice is what we need to copy. So if a minus coins of I minus 1 is more than equal to 0, if a minus coins of I minus 1 is greater than or equal to 0, then we're going to increment the value in table of I comma a. Now there is no row index here because it's just a single 1D array. So we'll say table of a is going to be incremented by the value in table of a minus coins of I minus 1. Right, the row index is implicit in the iteration number of this loop. So we just increment it by the amount a minus coins of I minus 1. So basically it's the same execution happening just on a 1D array. And we return finally the amount in, well, there's no row index now, just the amount in the column table of amount. So space used therefore is just order amount. The time is same as before, order n times amount. So this is one of those pieces of code where when you look at it, it looks pretty easy, but then the path to get there, if you have no idea how to solve this problem, is relatively long. But if you see this, this kind of code typically in dynamic programming, which is short and simple, but after you read, you can read it and then try to understand why it's correct. But that's not going to help you because understanding why something works after the fact is not going to help you solve a new problem. So, because it's unlikely that for a new problem you'll directly jump to a piece of code that looks like this. So you'll have to go through that thought process. And this is, I think, something I'm not sure if I covered this in the DP series, but I think coin change 2 I didn't cover. I'm covering it for the first time now. Maybe the knapsack problem was something I covered. Uh, but probably not to this level of detail. Multi-way inclusion um and converting that into binary include exclude choices and then collapsing it into a one-dimensional case. Uh, One of the other things to note about uh, these subset kind of problems is if these coin denominations are such that the values are quite large, let's say the last value is not 5 but 25 or 50 or something like that, then you're looking far to the left. Reshare. You're looking far to the left, and when you do that, one could argue that most of the values in the table might not even be relevant. So what I mean is, if let's say I want to find, I know this is the value I'm interested in, but my last coin has a denomination of 25 or 50. So that means this value is going to depend on a value that's far to the left. That means all of these values are never going to be used to derive my final value. Just because these denominations are so high that the amount of jump I make to the left is a huge jump. So if I'm going to be making these huge jumps, it's quite likely that in a few jumps I'll be hitting this wall. And if in a few jumps I'll be hitting this wall, but the table itself is really large, then I'm making this effort of filling in every single cell in the table, which might look like a lot of work, unnecessary work. So in such scenarios, it your code could run faster. Of course, it's hard to predict because it depends really on what values you're given. But your code could run faster if it was written in a memoized way rather than using tabulation. Because when you do memoization, you are only solving subproblems that are relevant to the final problem that had to be solved. Since you're going top down, you're starting from the actual problem that needs to be solved and then delegating the work and figuring out what subproblems need to be solved and getting their solution. Whereas in tabulation, you are solving all the subproblems where the first parameter varies from 0 to whatever the max value is, and the second parameter also takes those values. So it's more exhaustive. It doesn't use recursion, so that's one advantage, but still, in some cases, it might be a lot of work. So the last thing I want to do is to just rewrite this piece of code using recursion and then memoization. So that way, we basically uh, deal with this problem inside out in every possible way that could be um, written. So first, let's just work with this recurrence that we wrote and just quickly write the recursive code for it, which is going to be pretty short. It just has to simulate this recurrence, and we'll do we'll do the include exclude choice rather than the multi-way inclusion, so that the code is short and sweet. So we have to write the helper function first. So we have to write the code for a general worker in the hierarchy whose subproblem definition is that he or she is given an amount A to construct and uh, an index I in the coins array. Let's say this is, let's say, the index in the coins array, and amount A is the amount to be constructed, and let's say the coins array is globally accessible here. Otherwise you would just pass it as a parameter. So that's the subproblem definition, and first thing to do is to write the base case where the subproblem definition is essentially trivially small, empty. So uh, so if the amount that is to be constructed is 0, then we know that the answer is a 1. Right? That's why we had that wall of ones wherever the amount was 0 in the leftmost column. So if A is 0, it's ones. And secondly, if we have nothing in our coins array, right, that means our index I is not even pointing to a valid coin. For index I is not even pointing to a valid coin. I don't think the order matters here, but right, or you can say I less than 0. Then we return a 0. The recursive case, well, we have two choices: exclude and include, and we have to add up the counts from the uh, two cases. So let's say I'm just going to accumulate them in a result. So the exclude choice is where I make a call to a subordinate. Essentially, I'm excluding the ith, the coins of I. So that means I'm going to assign the same amount, but a slightly smaller coins index, right? Because I'm excluding the ith coin. So I will call with the same amount, but do away with the coin that I was focused on. And this value, whatever is returned, will be stored in a result. Actually, I don't need this. I'll store that in a result variable. And then the include choice is where I include one copy of coins of I. And I call a subordinate with an amount value that is smaller than A by the denomination of that ith coin. And because I included one copy, I leave it to my subordinate to figure out whether or not to include more copies. So my I index does not change. So this is analogous to picking a value from the left. This is analogous to picking the value from above me. So include, exclude, whatever the value here is, I'll just add it to the result. And then we just return the result. And if once we do this, this is the helper function. This is what a general worker in the hierarchy is calculating. So we need to execute this. So the root manager is going to just execute this helper function code with the right parameters. So the amount A is going to be whatever the actual amount variable was, and the index I in the coins array is going to be index, sorry, for the root manager. The root manager is given the entire coins array, so the root manager will start looking at it from the rightmost uh, coin. So that's index n minus 1, or length of coins minus 1. You could also do this from the left end, doesn't matter. Whatever the value here is, we'll return. So that's the recursive code. It just follows from the recurrence equation. Um, Memoizing this or memoizing any recursive code is straightforward in that we have a memo map which is just going to be an empty dictionary which initially has no solution stored in it. But so the two tweaks we have to make is when we are assigned any piece of work, we first look into the memo map to see if there is a solution, if that problem has been solved before. So I'm going to call this memoization case. If this if my subproblem definition is already present in the memo map as a key, then I will just look up its value and return that as my solution. Right? If my subproblem definition is a key in the memo map, I'm going to just return memo of that subproblem definition, which I'm looking up. I'm treating the subproblem definition as a key, looking up the memo map, which is like basically a hash table, and retrieving the solution and returning that. So I don't have to do any work. But if it's not present in the memo map, then I have to do all this work. But before returning the result, I should store it in the memo map as a key value pair. So memo of a comma I. So the subproblem definition as the key. The value for that is the solution that we are going to be returning. And then we return that. So that's the only, the standard tweak for memoizing a piece of recursive code. And this could run faster. It depends on what the test cases are and what the values are. And it's in such problems where you include and exclude, you have inclusion exclusion choices, and these, what you're including could be of such large magnitude that in one jump you might be going from the bottom right corner uh, all the way to somewhere here. So which means all of these values might not be relevant. Or at least many of those values might not be relevant. Okay, so that completes what I wanted to cover. I think we looked at least 3 or 4 different ways of writing the solution for this problem. But since tabulation is the most common, you would probably think of it from a tabulation perspective and space optimize it. But for subsets problems, there is always that possibility that memoized code might run somewhat faster. Okay, Pavan.
Hey, hi Omkar. So for the for the recursion, why aren't we checking that amount minus coins at I, right? Why aren't we checking if it is actually doable? Like for example, if we take your example of amount being 32, and let's
Mhm.
go with coin to be 5. So
Oh,
when we
sorry.
include
Yeah, that's a good catch. We should be checking. Uh,
uh,
so in the inclusion case, we should be doing that A, as long as A is greater than or equal to coins of I, we do this. Otherwise, we'll have a negative amount. Another way to do that is in the base case, say that if the amount is negative, then you return a zero. That's another way. If you want to avoid the check here.
all right, thank you.
Pratik?
Yeah, so in the memo case, would the space complexity be also less, even if we consider recursion stack?
Um,
Because this will only have the um, coins, the length of the coins, the size of the stack would be length of the coins array, right?
so space complexity is harder to say because even though there are fewer sub problems potentially being solved, but at least for this problem, you saw that the whole 2D table collapsed into a 1D array. So the space optimized version wasn't using that much space. So it might actually be, you
Right.
know, more space, less space used in the space optimized tabulation version than this kind of memoized code where you're using a hash table with pairs as keys and so on.
Will it depend on the amount? Like if the amount is larger, then the probably the 1D array would also be a large array. And in this case, so let's say if
Yeah,
the
yeah,
amount is larger, but the number of coins are zero or
right.
less.
Yeah, yeah. It could be. It could depend on the amount. So
Okay.
if the amount is huge, but the jumps are big, then memoization will use fewer pairs.
Okay.
Yeah, and if the coins are small and they are all of large denomination. Raghu?
Thank you.
Yeah, just one little thing. The memoization check we generally do before the recursive case, right? The base cases we would want to execute all the time.
I mean, if you include the base cases in the memoization table beforehand, then we don't even need to. Like for
Right.
example, here, if I could take these. Well, I guess if it was if a is less than zero, return zero. That can't be put in a memo table because
Yeah.
I need a specific key. But if
Yeah.
there are specific keys in the base cases, they could be put in the memo table, and then you can omit them
Okay.
from here. But you're saying we put the memoization case after.
After the base case is the way I've been doing it. Like before the
Uh,
recursive code, before making the recursive calls.
yeah. So yeah, it's a convention. I'm not sure if what are the implications, but I write it before, just like I write the backtracking case before the base case. So at the very beginning, you check whether the problem is even feasible. In this case, at the very beginning, you check whether the problem is already solved, and then only you. Yeah, I'm not sure it matters here. Right? It's just that you would be checking. It depends on whether you're hitting base cases more frequently or memorization cases more frequently. So yeah, it should be fine.